Yesterday in the discussion session, in the end, a couple of very important questions were asked. Why are we building these neuromorphic systems? What do we hope to gain from them? And what would be the killer application of these forms of hardware? So I'm going to address these questions more from the biology point of view, but then I think that the answer for neuromorphic hardware is going to emerge as a corollary. So yesterday in the discussion, I had to bite my tongue a little bit because I didn't want to spoil today's talk, but now you're going to get it. So we in the computational neuroscience community sort of span the entire range from abstract models that are theoretically well-defined and work very nicely, but as we heard yesterday, are difficult or inefficient to implement on classical backends, down to the biological substrate, which, as we know, is very difficult to understand experimentally and theoretically. It's very messy, but it's obviously very powerful in terms of computation and very efficient in terms of energy. Now, to get one thing out of the way at the very beginning, I would say that it's clear that if we have sort of some kind of inspiration from biology, some aspect in biology that we think is computationally very powerful, and then we transfer it to an engineering solution that is perfectly targeted to a particular problem, then obviously this solution is going to be better than anything that systems that adhere to biological, to being close to biology, will ever be able to achieve. But the question is, what are these principles of computation that are interesting and that we can take as inspiration from biology? And I think that in order to answer these questions, these types of machines are needed. And I'm going to get back to that at the end of the talk. One thing that we like to do in the neuromorphic community to motivate why we're building these machines is to quote Feynman, and this is this famous thing that was on his blackboard at his time of death. What I cannot create, I do not understand. And we are trying to interpret this as what I cannot build, I do not understand. Of course, we in the theoretical neuroscience community like to point out that actually Feynman was a theoretician. So what he meant was that if I cannot build a theory from scratch of a physical phenomenon, then I do not understand this physical phenomenon. So this talk is mostly going to be about theory and modeling.
That makes a lot more sense.
Right? So the first question, why spikes? This drawing on the right-hand side is kind of a metaphor of this. So of course, now that I live in Switzerland, I had to show this nice picture of the Matterhorn. And the plane with the wings, I think this is well known. The question is, if we want to make our systems computationally powerful, are we introducing spikes into the equation? Is it just like putting feathers on a plane's wings and making the plane flap its wings? One answer that is given very often, it was also given yesterday, is the energy argument. So it turns out that for communicating over particular distances, especially for long distances, there's an advantage to using spikes. But I would like to argue that there's also a clear computational advantage to using spikes. And actually, Mike hinted at this earlier in his talk. So I talked about these ideas a couple of years ago, 3 years ago, I think, at the NICE in Berkeley. But seeing that there are so many new people here, I'll just give a very, very brief overview of the concept of neural sampling. So clearly, since we have to deal with incomplete and noisy information about the world around us, we have to make some sort of inference, I would say probabilistic inference, about the reality underlying this kind of information. And there are two ways of representing probability. One would be representing it explicitly, so somehow storing probabilities. And the other way would be by sampling. So we represent states, and then by accumulating states, in the end, we accumulate knowledge about an underlying probability distribution. And this is just a cartoon to show how this could be working in the brain. You can either see a duck looking to the left or a rabbit looking to the right, but you're never going to be able to see the two at the same time. So you're essentially sampling from a bimodal distribution over the two possible realities, duck or rabbit, that underlie this kind of duck-rabbit illusion. This can be done with spiking networks, and this is actually the most natural way to do this because spikes or bursts actually represent changes in states. So again, you can look back at the things that I said in Berkeley of exactly how this is implemented, but this is the first idea. Spikes represent states. This is the most natural way to represent sampling. This is just an example of a spiking network, hierarchical spiking network that we trained with handwritten digits. And you see that it's dreaming over here, so it gets no input at all. And you can see that it's stochastically changing its state. That's what it's supposed to do. And the interesting question now is, where does this stochasticity come from? So in many models, in general, probably most people in computational neuroscience, just assume that neurons are either intrinsically stochastic or somehow stochasticity is injected from the outside, say as some spike trains. So how would you generate stochasticity in a physical system? Because we know that neurons aren't really stochastic on their own. You could think of continuous dynamical systems that generate chaos, and this probably all know this. This is the Lorentz butterfly. The problem with generating chaos in continuous systems is that you need very, very specific parameter values, or you need to be somewhere in a very small volume of your parameter space to do that. So the much easier way to generate chaos is in discrete systems. And for example, this is a classical implementation with a discrete system, linear feedback shift register, of pseudo-random number generation. Now, you could argue that you could have one of these things in every artificial neuron, but on one hand, nature doesn't do that. And on the other hand, this is not really a parsimonious solution. So what I would like to suggest is that functional networks in the brain that require stochasticity get this form of stochasticity from the larger network, from the brain itself, in which they are embedded, in the form of spikes. A problem that arises here is the fact that multiple neurons are going to share sources. So this is going to induce correlations in the spiking activity. So these networks will sample from a different probability distribution than they are supposed to. But it turns out that in excitatory-inhibitory networks that are dominated by inhibition, these networks are going to generate a form of spiking activity that is intrinsically negatively correlated, which will automatically, naturally cancel out the positive correlations that arise from shared inputs. So this would be a situation where you don't have this mechanism in effect. The network is going to sample from a distribution that is different from its target distribution. This is not very close to zero. Whereas with this kind of embedding in a background spiking network, you get sampling from something that is very close to the target distribution. This is also a very efficient solution in terms of the size of this thermal reservoir, if you will, because you can make this reservoir extremely small without losing sampling accuracy, and only at very, very small sizes do you get problems because essentially the activity of this network is going to freeze. Now, I mentioned parsimony a minute ago, and you could argue, well, this is not a really parsimonious solution either, right? Because you need a lot of, or a certain number of background neurons that generate this. Well, but nobody says that this network over here doesn't have a function of its own. So this would be a picture that is probably more likely to be what's happening in the brain, where you have a couple of functional networks that, say, perform stochastic computation, but that feed each other with their own functional activity as stochasticity. So here we have a computer simulation of 6 hierarchical sampling networks that are fully deterministic. There is no noise injected here, just a moment. And that are dreaming from the data that they have been trained on. And dreaming is sort of the ultimate form of pattern completion because there is no input at all. But for example, if you show these networks this kind of arc over here, then they're going to do correct Bayesian inference and complete the digit. In this case, we trained them on handwritten letters to either an R or a B, both being compatible with this input. So this is Bayesian inference. You had a question, Kovena.
Yeah, I mean, what about probabilistic synaptic release? I mean,
Yeah, this is... everybody asked this question. So there are 2 reasons, I would say even 3, why this is not a good solution. First of all, there is no good theory of how you would describe the probability distribution from which a network with stochastic synapses would sample, and in particular, how you would train this target distribution.
But isn't it a source of noise that is uncorrelated?
Second answer. This source of noise is very high dimensional compared to the stochasticity of neurons themselves. So this makes search in the solution space tricky. Third answer. It's difficult to implement in hardware. Stochastic synapses. So to have stochasticity in each synapse where the form, so the nature of the probability distribution from which each synapse samples is well defined and precisely defined, I would say that this is pretty difficult. And now, surprisingly, you can make this idea work with a single network. So this is a single stochastic spiking network. All these networks are essentially modeled after Boltzmann machines, so you could say that they are spiking Boltzmann machines, although there are important differences. They are restricted in the sense that there are no horizontal connections, so within layer connections. But by adding these connections, we can make a fully deterministic ensemble of spiking neurons dream nicely from the data set that it was learned. Again, this is a fully deterministic network of spiking neurons. This is the same thing on neuromorphic hardware. It's a set of 15 spiking sampling networks that are trained on the brain scale system to sample from each from its individual target distribution. You're going to see that some of them aren't doing very well. This is what you get with an analog substrate, but most of them are doing the right thing. I would like to draw your attention to the time scale over here. You cannot read the numbers. I'll read them out for you. The system converges on the scale of 10 to the 4th to 10 to the 5th milliseconds. So that's 10 to 100 seconds in biological time. In hardware, that's 1 to 10 milliseconds. So keep that in mind for the end of the talk, where I'm going to argue why neuromorphic hardware is important. One more thing. You can see that this network dreaming from digits, from MNIST digits, or dreaming of MNIST digits, rather, switches nicely between different digits. This is called mixing. And if you did the same thing with a Boltzmann machine with identical parameters, you wouldn't get that. It's going to be stuck in a local mode. And the reason is that training, contrastive divergence training, actually promotes deep local modes of the energy landscape. This is another example of one of these spiking networks trained to play Pong. So you can see how it nicely predicts the trajectory of the ball. And it also has this kind of searching behavior, which is another useful feature. The reason why these networks can do that, the classical networks can't, is, again, because of spikes. Namely, spike-triggered short-term synaptic plasticity. You have synaptic depression, meaning that an ensemble of neurons that is currently active is going to get weakened over time, and it's going to push the network out of its local mode and into a different mode. Something similar can also be done that is even closer to annealing with brain rhythms. So you can show that spiking networks under certain circumstances generate oscillations. And these oscillations are analogous to annealing. And this is how you get mixing in spiking networks again. OK, this concludes the first part of the talk. The second part is about gradient descent. Another beautiful picture from Switzerland. The idea here is that water tends to accumulate in the valleys because this is what gravity does. It does essentially gradient descent on actual mountains. So how would biology be implementing this kind of physics is a relevant question for understanding how the brain is able to learn. Gradient descent, I should say Euclidean gradient descent, we know that it works nicely, but you can see that it's pretty inefficient because it takes a crooked path towards the local minimum instead of going straight. With neurons, it would mean the following thing. If you have two synapses along a dendritic tree that are sort of equally important for the thing you want to learn, and one is closer to the soma than the other, then the synapse that is closer to the soma will have a larger impact and is going to learn much faster than the other one. So the path in parameter space is going to be crooked. One synapse learns quickly, and then the other one learns very slowly to get to the local minimum. This is a geometry problem, and it has something to do with parametrization. So this is an illustration of why this kind of Euclidean gradient descent is inefficient. If I show you this particular projection of the Earth's surface, and I would ask you to draw the shortest path from, say, Europe to Canada, then you might come up with this straight line. And if I showed you a different projection, you might draw this straight line. Now, it turns out that, first of all, the two lines, the two paths are different, and secondly, none of them is optimal. So in order to get the true shortest path, you have to take into account the geometry of the system. And you do this by looking at multiplying the metric tensor that is characteristic for this particular geometry. When we're looking at output distributions of, say, spikes, that particular metric tensor is the Fisher information matrix. So we can do all the math and derive a learning rule. I'll come back to that in a moment. But the intuition of what this learning rule does over here is the following. It transforms the energy landscape that is weird with different mountains and valleys. It transforms it, at least locally, into a cone. So wherever you are in the cone, you will always, just by following gravity, go down towards the minimum along the shortest possible path. So this is what you see here. This is the crooked path that the system took before with Euclidean gradient descent, and with natural gradient descent, you go directly to the minimum, which makes it more efficient and faster. What does this learning rule do? This term over here, this is the target of the neuron, what the teacher tells the neuron to do, minus what the neuron actually does, minus its membrane potential. This thing over here has something to do with the activation function of the neuron, and this is the presynaptic firing rate. So all the terms over here are purely local. This is the Urbanchik-Zen learning rule. So this is biologically plausible and can be implemented in other physical systems that require locality, such as neuromorphic hardware. These other terms over here are also local, and they make the difference between Euclidean gradient descent and natural gradient descent. And now now that we have a theory of learning with natural gradient descent, we can go back to biology and see what this theory predicts. And it would predict, for example, that synapses that are farther away from the soma tend to be bigger. This is called dendritic democracy. This is exactly what we observe in some areas of cortex. It would predict that larger synapses change faster. Indeed, this is what is observed. And finally, it would predict that synapses that don't get input also learn when other synapses do. This is called heterosynaptic plasticity, another thing that is observed in biology. OK, so now we can get one neuron to learn efficiently. But the most important problem, of course, is how do you learn across hierarchies? So the question of how could the brain be doing backpropagation, this is not an artificial question. It's not like we know how to do backprop, now let's try to do it with spikes just because our neuromorphic systems happen to implement this kind of dynamics. But this is a really fundamental question. How can the brain solve the credit assignment problem? How can I change weights in V1 if in my prefrontal cortex I know that I have a wrong prediction? The second problem is, how do I do this in continuous time? Because you see, classical backprop would require me to take a look at this room, then close my eyes, wait for the activity to propagate all across my cortex, then change my synapses, and then open my eyes again and take in a different image. This is obviously not what we're doing. So in order to solve this problem, let's take a big step back, and think a little bit about physics. Really just, first of all, without any connection to biology. Assume that I drop a ball that is elastic. You all have an intuition of what it's going to do. It's going to bounce and then get closer and closer to the ground. It is not randomly going to jump to some corner of the room and then get back, or take a crooked path and then go back to the straight path. There is something very natural about trajectories. And that is that trajectories in physics, in all of physics, obey some sort of shortest path law. It's actually the principle of stationary action. So what you can do is you can define the energy of a physical system, translate it into a Lagrangian, this is just a formalism, and then require that the action of this system is minimal. And from this you can derive the laws of motion of this system. For example, the laws of Newtonian motion. We know that this works in all of physics. There is no reason whatsoever why it should work for high-level quantities such as membrane potentials. It works certainly for the interaction of atoms in a neuron. There's no reason why it should work for ion flows, but we could just try. Now, you'll have to forgive the mathematics, but it's actually much more intuitive than it looks. So assume that you have a hierarchical network of neurons, and you want to encode the error of this network as an energy. These terms over here are just the difference between what a neuron does minus what its presynaptic partners from the layer below tell it that it's supposed to do. You take a square over this because it's supposed to be positive, and then plus the activity in the label layer, where you have, again, the membrane potential of the neurons minus what the teacher tells them that their membrane potential should be. So this is a very, very natural and intuitive way to encode error as an energy function. Now you need another step here, because neurons in biology don't just fire depending on their membrane potential, but they also fire depending on the temporal derivative of their membrane potential. So you include these dynamics, and in the end, you get a Lagrangian from which you can derive equations of motion. And I'll come back to those immediately. And by minimizing the energy in this system, so by reducing the error, you can derive a plasticity rule. The intuition behind this is the following. If I have no teacher, then my network is going to follow this blue trajectory. So it's going to reside in the zero energy state. It's going to do something, but with zero energy. As soon as I have a teacher, the output of the network, or the label that the network predicts, is probably going to be different from what it's supposed to do. So it's going to be driven up the mountain. And what synaptic plasticity does is drive the trajectory back down the mountain into the zero energy or zero error valley. So we can now solve these equations. And again, these look much more complex than they actually are. This equation down here, tau u dot is equal to the input minus u. This is a leaky integrator. Plus this error term that comes from layers above. This is backpropagation. And the learning rule that we derive from minimizing the energy, this is exactly the Urbanchik-Zen learning rule that I mentioned before. This is just an error-correcting, fully local plasticity rule. So from a very abstract representation of errors, we can derive, using the Lagrangian formalism, network dynamics that look very much like we have both in biology and in artificial systems. Without going into detail, this is just to show you that the calculation of errors, the weird error term that I mentioned before, can be performed by a microcircuit that only requires local computations. This is one thing. And the second important ingredient here that I only mentioned briefly is the fact that the firing rate of neurons depends also on the derivative of their membrane potential. So the neurons are able to undo the low-pass filter that they have to perform on their own inputs. So this Lagrange formalism performs just as well as backprop, and if you also add recurrent connections to the network, you can also learn temporal patterns. So coming back to the first slide, I hope that I was able to convey the idea that if you look at particular aspects of biology, you can actually gain computational advantages for artificial implementations. And clearly, at this point, I would say that the development of neuromorphic systems, the importance of this development, is a pretty obvious corollary of what I said before. Because if I want to test a hypothesis about computation biological systems, then I want to do this quickly. And I want to do this on a large scale and hopefully being able to pay the electricity bill. So these systems used as tools for analyzing biologically inspired superior, I would say, forms of computation is the killer application for neuromorphics that we asked for yesterday. Another point that we'll have to leave for a different talk is robustness, because in particular in analog neuromorphic systems, you are forced to build network models that are robust to noise. At the very end, this is probably the most important slide. The people who have contributed to this, it's a very big team of people, as you might assume, because I touched on several very different topics. So we have from Heidelberg, Dominik Dold and Akos Kungel, who worked both on the stochastic sampling, spiking sampling networks, and on the Lagrange formalism. Andy Baumbach from Heidelberg, who worked on the sampling networks. Agnes, who was with us a couple of years in Heidelberg, and now she's in Jülich. She worked on the annealing with rhythms, with background oscillations. Luciwei Leng, who worked on short-term synaptic plasticity from Heidelberg. Elena Kreuzer in Bern, who worked on natural gradient descent. Oliver Breitwieser, who is still in Heidelberg, and he wrote essentially most of the code for all these applications. Jakob Jordan from formerly Jülich, now he's in Bern, worked on the embedding of sampling networks into thermal reservoirs. João Sacramento, who was a couple of years with us in Bern, now he's in Zurich. He worked on the microcircuit model for biologically plausible backpropagation. And then I should mention two people who aren't on the slide, but who are here in the room, Sebastian Schmidt and Erik Müller. There they are. Without them, probably nothing on the hardware would work. And finally, the theoretical mastermind from Bern, Walter Senn, the father of the hardware in Heidelberg, Johannes Schemmel, and of course the one and only Karl-Heinz. Thank you very much.
Thank you, Mihai. We have not really time for questions, but one question is mandatory.
Two things. One is your assumption is that there is no natural stochastic variation in synaptics. And if you look at the ion exchange, it's kind of true. It's a chemical equilibrium that has its own symphony that it goes through. But there are variations in coming from the surrounding environment, that is an enzyme that other systems are secreting that influences that balance. So on one hand, you are saying that there is no stochastic variation. On the other hand, you're saying that there are surrounding systems that are inducing stochastic variation into that system.
Okay, so The form of stochasticity that you mentioned acts on very long timescales. I'm talking about stochasticity on short timescales, from spike to spike. If you're talking about enzymes and diffusion of chemicals and so on, this is a slow process. I agree that that's stochastic, but on a totally different timescale than the things I discussed here.
Okay, so then there is, if a synapse surrounding it, it's, so I agree that that's different times.
And by the way, just sorry for interrupting, but all of the networks that I presented in the end of the first part were fully deterministic. There was no stochasticity there whatsoever. Even in the thermal reservoir, this was a deterministic network of leaky intermittent fire neurons. This is important. So this is stochasticity from deterministic systems.
Okay.
And this can be achieved because of spikes, because they are sort of discrete.
I understand. It's a longer conversation.
We have a lunch break for discussions. Thank you again, Mihai.